In this video, I'll talk through the Advanced Higher Chemistry 2025 paper, explain how I would approach each question. Starting off in the multiple choice with question number 1, we're asked about the hydrogen emission spectrum. This is when energy is released, and that's as the electrons relax and fall to a lower energy level. A is describing that, and excited electrons dropping, releasing energy as it goes. That's going to be our answer. Lies within the visible spectrum, where we're at values between 97.3 and 121.6. If you're unsure of the visible spectrum, we can look at page 19 of the data booklet to see the visible spectrum. That's from 380 to 750. We are not within the visible spectrum. That's not with that answer. If the electron was moving to a higher energy level, it would need to absorb energy, which is not what's happening here. This isn't representing the individual energy levels, it's showing the transitions between different energy levels. A is our correct answer there. In this one, we're given a diagram of an orbital. If we had an s orbital, it would be a sphere. We do not have them. If it was going to be a p orbital, they would be dumbbell shaped, orientated along an axis, which is not what we've got, so it's not going to be a p orbital. We have been shown specifically this orbital in this middle. This is a specific d orbital. There isn't one shape that covers all of these 5 different orbitals. If it was talking about a p orbital, if you were not given axes to show the orientation, then it could be any of the p ones. As it is for this question, we were given a specific d orbital. Next one, we are asked about an ion, which has a certain number of electrons. We're asked about the blocks in the periodic table. First thing I would do is, what if it's x3 plus with 55 electrons, and the atom itself would have 58 electrons. Number 58 is down at the bottom. It's part of the lanthanides. In terms of our blocks, the first 2 groups are part of the S block. We then have the P block, A block, and down at the bottom we have our F block elements. This means our answer is F block, making the answer D. And here is the diagram showing those different blocks, S, P, D, and F block. If you had not remembered to add on 3 more electrons, you might have thought that we were dealing with cesium, which would have made it an S block, but the correct answer here, F block. Here we're looking at the electron pairs around sulfur in sulfur tetrafluoride. First thing we need to do is figure out how many pairs of electrons there'll be. We look at the number of valence outer electrons on sulfur. Sulfur is in group 6, therefore it'll have 6. Add on 4, because there's 4 things connected. That gives you 10 electrons, which is 5 pairs. That takes our answer down to B or to D. Next thing, we're asked about the shape that would be adopted by the electron pairs. In a question like this, we do not care about the fact that only 4 of them are bonding. It's just the fact that we've got 5 pairs of electrons, and if there's 5 pairs of electrons, you'll have trigonal bipyramidal shape, which makes B the correct answer. If the question was asking us about the arrangement of the atoms around the centre, that would be a different answer, where we do then consider if there are lone pairs which would have an effect on the arrangement. If there were 4 pairs of electrons around the sulfur, we would have been in a tetrahedral shape. So C would be correct if there were 8 electrons and therefore 4 pairs of electrons. If you find it difficult to visualise and remember what the different shapes would be, I'd strongly recommend the PHET, PHET molecule shape simulation, where you can add in different numbers of bonding pairs like we have got here, and also lone pairs of electrons that will affect the shapes of them. Down at the bottom, the electron geometry is regardless of bonding versus non-bonding or lone pairs. In the molecular shapes, they are taking into account these lone pairs that will distort the shapes of them as well. And we can see we've got baseline shapes of linear, trigonal planar, tetrahedral, trigonal bipyramidal, and then also octahedral. Next one, we're looking at the colours of light that's being absorbed by a transition metal complex. And this links to the D to D transitions. In order to answer this, we need to look at the colour of light absorbed. We go to the colour wheel and we look for the complementary colour. So we've got blue and we've got green. So opposite from blue would be yellow, and opposite green we have got purple. And this is the colour absorbed. So going from yellow to purple, we have got a smaller wavelength of light. If there is a smaller wavelength, that's going to be a higher frequency and a higher energy. So we have an increase. We have an increase in the energy of light absorbed. And the reason that we need a higher energy photon of light absorbed is because there must be a bigger gap between the d orbitals. There has to be a bigger splitting of the d orbitals, and that makes my correct answer A for this one. So the longer, higher the energy of the light absorbed corresponds to a bigger energy gap between the d subshells. Next question is building off of that. We have got our orbitals that have been split, 2 higher energy and 3 lower energy. This seems like it's going to be a bit of a tricky question. What we've been told is that in an octahedral complex, the ligands lie along the axes, and this is the splitting that happens. So if we're lying along the axes, we've got 3 lower energy and 2 higher energy. In a tetrahedral complex, the ligands lie between the axes. I like the energies of the d orbitals in a tetrahedral complex are. And transition metals, so there is electrons in the ligands and electrons in the d orbitals, so there will be some splitting. This would be when the metal is by itself. I'm going to go for a splitting. Now, a big part of me just wants to get rid of this one because it looks absolutely horrific. There will probably be a reason why it's not that, but I'm just saying that just looks wrong in all ways, shape, or forms. The ligands lie along the axis in the octahedral, and then between the axes in this tetrahedral one. So it's unlikely that they're going to be split in the same way as each other because there's a difference in their orientations along the axes. So our correct answer then is going to be C, is what I'd go for there for that. So because there's a difference in the splitting, because there's a difference in their orientations, there would be a difference in the splitting. They're still going to split, but in a different way. So here we've got 3 higher energy and 2 lower energy. So I'd make my answer C for that one. That is a lot different from the typical standard question, which would be us giving the free ion by itself, and it asked to turn it into this one here. So C would be my correct answer for that one. Next one, we're talking about the oxidation numbers. If we are in a free atom or molecule, the oxidation number will be 0. For our right hand one, well, we've got sodium. Sodium is in group 1, so that will have a charge of 1. But we've got 2 of them, so that's going to be 2 positive. We have sulfurs of unknown values, and we've got 2 of them. And then oxygen is going to be 2 minus, and then that's going to be 3 of them. So that's going to be 6 negative. We have got no charge overall, so we have to find a number that would go here to balance it out. So that would be 4 positive. If we need 4 positive from the sulfurs, each sulfur would have to be 2 positive to give you an overall 0. So our correct answer here should be A. If, as one of the options says, this was 4 positive, well then this would give you a total of 8 positive. Then you would end up with 10 positive and 6 negative, giving you overall 4 positive, which is not what we see up here. So because it has to equal 0, the overall charge, 2 positive on sulfur would have to be correct there. Next one, we're talking about a Brunstad or Lowry base. An acid is a proton donator. A base is a proton acceptor. Narrows me down to C or D. When the base accepts the hydrogen, it then becomes the conjugate acid. So the name flips over. So acid becomes conjugate base, and base, as in this question, conjugate acid. Next one, we're asked to calculate the pH of a buffer solution. We're going to go to the data booklet. So the buffer solution is pKa minus log to the base 10 of our acid over our salt. Our acid is butanoic acid, so let's find the pKa of that. 4.83 minus log to the base 10. We've got two concentrations. The acid goes on top. So 0.1 over 0.2. And pH equals 4.83 minus log of 0.1 over 0.2. Gives an answer of 5.13. It is an answer. It is an option. We'll pick that for answer D. Next one is we're asked about the lowest pH, and this is to do with the combinations of strong and weak acids and bases. So sodium chloride is likely came from the formulas. So sodium hydroxide, NaOH, and HCl. That's strong and strong. So likely pH 7. Again, likely going to be a strong base. And then this will come from carbonic acid, CH2CO3. And if it's strong base, weak acid, pH will be likely above 7. Or NaOHs that we've got in that one. Now, something to watch out for here is we're talking about SO3. So it's not going to be sulfuric, which would be H2SO4, which would be a strong acid. We're dealing with sulfite, which is from sulfurous, so SO3 minus, which is a weak acid. Anytime you're unsure of if it's sulfate, sulfite, or anything like that, page number 9 can be helpful just to figure out which one we're dealing with. Again, that's going to be H2SO3. That is going to be similar, strong and weak. So pH above 7. Last one, 2 carbons. It's an carboxylic acid. That's going to look like ethanoic acid, so CH3Q. Same again, strong and weak. So although it's asking us for the lowest pH out of these options, it would be A, even though it's still going to be pH 7. It's not going to be acidic. To be acidic, you need strong acid and weak base, so A is the correct answer there. This one will really test your knowledge of your weak acids that they can ask us about. Next up, we're talking about strong versus weak. So ethanoic acid is weak and HCl is strong. Okay, so we have to focus on the weak acid, and it's weak because it's partially dissociated. So what does that mean? Well, that means that less of their hydrogen ions would have been released. There's less H pluses that will have it'll be less acidic, so it'll have a higher pH. Again, because it's partially dissociated, not all the ions will be free, so not all of them will be available to carry the charge and conduct the electricity, so it's going to have a lower conductivity. Oh, 2 options of both that, so I don't actually need to look at that one. And then in terms of their rate of reaction, well, a weak one has got some of the hydrogen ions hidden away, so they'll react more slowly with the magnesium, making our correct answer B. If it was talking about how much magnesium it could react with, you would still react with the same quantity of magnesium, because as the H pluses are used up in the weak acid, it then dissociates more to replace them. So you end up with the same product, volume of product produced, but the speed, the rate at which that happens would be slower for this one. Next one, we're looking at the overall order, and this is based off the rate determining step. And then what we're looking at is we're looking at how many molecules of, we're looking at moles of reactant in that rate determining step. 2 plus 1 gives you 3. The overall rate will be third order. Next question, we're asked about the standard enthalpy of formation. It's the energy released when 1 mole of a substance is formed from its elements in their standard state. What I'd first do is check that we're making 1 mole of our calcium nitrate. All 4 of them are doing that, so we can't rule any out. Looking at the chemicals we've got, well, calcium is a metal. It's going to appear as a solid at 25 degrees Celsius. So that would rule out these two. Nitrogen exists as a diatomic element, which means it's not going to be A, because it's going to be N2, not 2N. Oxygen as well is diatomic, which is going to lead us to the correct answer of D. If you're unsure of whether something would be solid, liquid, or gas at room temperature for these questions, you can go to the melting points and boiling points page in the data booklet. Calcium has high melting points and boiling points. We are at 25 degrees, so it's not going to have melted. It's going to be a solid. And then the two gases involved have low melting points and boiling points, so that would be our correct answer there. In this next question, we're asked about delta S. Delta S is entropy. Delta S is disorder. Gases are more disordered, as shown by this animation, as shown by this simulation on eChalk. When we move from solids to liquids, they are taking on energy and they are becoming less ordered. They're moving around more as it goes. And then as you then go past liquid into a gas, they're becoming even more disordered. The entropy is increasing with increasing temperature. Looking at the options in the first one, we have got gases all the way through. So the disorder, therefore, is not going to be changing. Next one, we've got gas and liquid going to a liquid. So we're losing a gas, so it'd become more disordered. Nope, it'd become less disordered. Not our answer. Next, we have solid and liquid going to solution and a gas. That is going to be an increase in disorder and entropy. And here we're going solid and liquid. We're cooling it down, less disordered. Correct answer, C. Here we're looking for our sigma bonds, which are the first bond that every atom makes. We should check if there's going to be any hydrogens, which we would have one there, 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 and there. Nitrogen makes 3 bonds, so that's all good. So in the ring, we would have 1, 2, 3, 4, 5, and 6. Then 7, 8, 9, 10, 11 in total due to the hydrogens that are being attached. And that would give us the answer of C for number 15. Next up, which is following is not true for these two chemicals. We should recognise that that is an alcohol and that is an ether. How can they be made? Well, they can both be made from a haloalkane. So if we have our chemical with our halogen, if we replace that with an alkoxide reagent, we would make our ether with the oxygen trapped between two carbons. If we used something like sodium hydroxide, that would be replacing the X with an OH. So they are both possible. So is true, not our answer. For the next one about hydrogen bonds, for them to have hydrogen bonds between themselves, they would have to have an OH. So to answer question B, we're thinking back to higher when we talked about the fact that you need a hydrogen bonded to an O, F or N to have hydrogen bonds between their molecules. And ethers do not have that. Therefore, ethers cannot form hydrogen bonds between their molecules. And that's going to be our answer for that. The thing to watch for, and this is one of the questions a year ago or a couple of years ago, was that they can both to water. So because of their lone pairs, they are able to make hydrogen bonds with water, but not between themselves. So not ether to ether, but ether to water would be able to do it. If we look at their formula masses, we would need to have a wee sketch of them out. So you get 2 carbons, an O, and 2 carbons. You would have all your H's around it. You would have C4, H10, and then O, and then butanol, 4 carbons, C4, H, 7, 8, 9, 10, and O. They have the same formula, they will have the same gram formula mass, so it's not going to be that one. They are very flammable, so ethers have that whoosh, quick, fast flame, alcohols you've used, burning them to work out the energy release from them. So they are both flammable, so that rules them out as well. A, C, and D can all be proved relatively easily. They are all facts about these two chemicals. B is going to be the answer to pick up our mark. Next one, we're asked about tertiary. So we need to be focusing in on, first of all, the carbon that has the bromine on it. And in this one, we have the nitrogen that has three things, or things joined onto it. So we have got 3 carbons attached to the carbon with the Br. Here we have 3 carbons attached to the N, directly to the N in this case. That is going to make both of them tertiary for that one. Aha, yes. So how they almost tricked me there. I was looking at B and I was going, actually, but that looks like it's got 3 carbons. That's not where we should be looking. We should be looking at the nitrogen. So look at the nitrogen. There is only 1 carbon attached to the nitrogen for that. So that is going to be a primary amine for B. Over with the bromo, that is 3 carbons attached to the carbon with the Br. So that would be a primary and a tertiary, not both of them. That's not going to be our answer there. Next up, we need to look at the carbon attached to the bromine. It's only attached to 1 other carbon, making that bit primary. And on the other side, we have got a tertiary amine because there are 3 carbons attached to the nitrogen. Next one, we have to look at these points. There are 2 carbons attached to the nitrogen, making that secondary. And in this one, there are 2 carbons, making that one secondary as well. It's a bit awkward because with the carbon to bromine or carbon to oxygen, we look at the number of carbons attached to the carbon with the OH or the Br or whatever it might be. Whereas for amines, you look at how many are directly attached to the nitrogen. So there's a little bit of a difference between the two of them, but hopefully you would be able to pick up that it's A for number 17. Number 18, we're asked about what type of reaction we have. If it was addition, we're looking for carbon to carbon double bond breaking. That is not what we have. A nucleophile, so let's look at what we've actually got. So do we have, our benzene ring has lots of delocalized electrons and it will undergo electrophilic substitution. So we are looking for something that would like electrons. So it's not addition. Well, this would act as a nucleophile, but that's not what's happening in this reaction because we're attacking something that has lots of electrons. The electrophile comes in and attacks onto the benzene ring. It's the NO2 that has came in and attached to the benzene ring. So the NO2 positive acts as an electrophile. Benzene undergoes electrophilic substitution. It's what the substitution is happening to, not what's doing the substitution reaction. Geometric isomers are mirror images of each other. That sounds more like they're talking about in optical isomers, so non-superimposable mirror images. Optical isomers always contain a carbon-to-carbon double bond. That is not true, but they have restriction of rotation. Restriction of rotation. That can either be by a carbon-to-carbon double bond or by a ring structure. So you can get that in a different way. When we're dealing with our cis and our trans, they will have slightly different physical and chemical properties. Some might be able to react with certain chemicals and other ones that they won't. They have 2 different groups attached to each of the carbons of the bond with restricted rotation. So that is exactly what we were talking about. That would pick up the mark for that one. Next up, we are asked to work out which contains the greatest number of negatively charged ions. Job number 1 would be get the number of moles, so N equals C times V. Remember to turn your centimeters cubed into litres. That's just how many moles of each chemical we've got. We then need to think about how many negatively charged ions are within each of these chemicals. Give ourselves a little bit of space then. So this would be Fe3 plus Cl minus, but there's 3 of them. That means we need to times the number of moles by 3 to figure out how many moles of the ions there would be. So 0.072. Next one, it's just K plus I. So that would just be times 1, so it stays the same. Next one, it's said in 2 positive. Nitrate is -1, and there are 2 of them, so we need to double that up, 0.08. And then it's Na positive, 2 of them, SO4, 2 minus, times that by 1, stays the same, 0.05. That gives us correct answer of C. So 2 parts there. I'll work out the number of moles, which should be almost automatic from having done it previously. Look at the formulas of them, think about the negative ions, and that would hopefully help us get the answer there. Next one, what type of radiation is used to produce an NMR spectrum? That feels like it's just one of those facty ones that it is to do with radio waves. So this would be for infrared spectroscopy. And then with your visible and ultraviolet, that can be used to look at the wavelengths of light that's absorbed. So absorption spectroscopy, colorimetry, spectrophotometry, something like that. UV vis spectroscopy would be that one. So E would be the correct answer there. Next one, a primary standard. We would be looking for a base. Potassium dichromate oxidizing agent. I won't lie, no got Scooby-Doo, don't know. Potassium hydrogen phthalate, no idea. Hydrogen sodium hydroxide then is not a primary standard. It's got too small a GFM, it absorbs water. It's not suitable for this use, whereas the sodium carbonate would be the correct answer in this question to be able to make that work. I'm not sure exactly why the last one's ruled out, but B would be my correct answer. When it comes to melting points, pure samples have narrow bands. That rules out for me A and C for that. Impurities lower it. So if we're getting rid of the impurities, then that would mean it would go up. Give us an answer of D for number 23. Next up, we're asked for a suitable filter for this. Well, if the substance is orange, well then orange absorbs the complementary colour, which just from the options I would presume is green and blue. I would obviously definitely check it and not just go off of it, but orange, blue, green, they are complementary. Okay, so solution of this. Now, was this going to be because this is just carbons and hydrogens? That will be non-polar substance. And non-polar dissolves in non-polar solvents. Water's polar. So our answer then should be E, because it wouldn't dissolve very well in water because it can't form hydrogen bonds with the water. So B for that one. Next one, we're talking about recrystallization. Are these ones as well? Okay, so dissolve the impure sample for that. Okay, so if we are dissolving it in hot volume, so the idea would be our sample dissolves. The stuff we want dissolves, which would mean it would trap any impurities. So when you filter it, you filter off any impurities that haven't dissolved for that. We're then cooling it down and letting our crystals form. And then when you're filtering it, that will keep our chemical crystals that we want, keep them, and anything that's still dissolved, that's an impurity, would be removed. So 4 would be the third one for that as well. So we dissolve, we are hoping that in stage 1, our chemical goes into solution. passing it through leaves behind any insoluble samples. If other chemicals have came over into our conical flask, by letting our chemical dry and become a solid, we can then remove that from any left over in the filtrate in the solution for that. So that should give us an answer of C. Moving on to section 2. First question, we're asked about optical isomers. This is what I said earlier when we talked about geometric. They are non-superimposable mirror images of each other. So easiest way I find for drawing out the isomers of them is to keep the part at the top. It's our CH2COOH. And have that coming down. We've then got our hashed line going down into the left. So we want to have our one down and to the right. We've then got our wedge going down into the left. Let's make that go down and to the right. Then we've got a normal bond going down to the right and the original, so down to the left. And the other one, when it comes to telling them apart, it's all about how they rotate plane polarized light. They will rotate by the same angle in opposite directions. When you have an equal mix of both of them, no effect on plane polarized light, because if one's trying to rotate it to the left, the other one's trying to rotate it to the right, if there's the same quantities of them that won't do anything, that is described as being a racemic mixture. Each of them are called enantiomer, so equal concentrations of each enantiomer will be described as a racemic mixture. Next one, we're asked about how a pi molecular orbital is formed. The pi ones is from a side-on overlap of orbitals. If you're asked about sigma, sigma is from the end-on overlap. Next one, state one conclusion about the structure of phenols and acid strength. So stronger acids have higher Kas, equilibrium dissociation constants, and lower pKa. That's because pKa equals minus log to the base 10 of the Ka. Okay, so which ones can we compare? Okay, if we're dealing with those ones, well, phenol. Okay, so if we look at them, if we go from phenol to 3-hydroxyphenol, that's an extra hydroxyl OH group. So we've got one OH, two OHs, and then three OHs. The pKa is going down, which means that it's going to be a stronger acid. So more hydroxyl groups, stronger the acid from the ones down here. If the methyl group's on position 4, it has a lower pKa, so it's going to be a stronger acid. Or if we're just comparing the length of the branch, so longer branch is the stronger acid. Next question, we're asked to work out the concentration of H3O positive in this particular weak acid. So when it comes to the weak acids, we need to use half pKa minus half log base 10 of C. That means pH is going to equal a half of, so 2-methylphenol, so 10.29. Minus half log base 10 of 0.15. That means that pH equals, well, popping out the calculator, we get this. I would round that to 5.557, we'll say, for this one. And then if pH equals minus log to the base 10 of the hydronium ion concentration, rearrange that for rearrange that for working out the hydronium ion concentration. We 10 to the power of minus whatever that value was. Plug that in the calculator and we get an answer of 2.77 times 10 to the minus 6 moles per litre. Okay, one bit I would do is let's look at the colours that they will absorb. So violet and orange. If it appears violet, it absorbs yellow, green. If it absorbs orange, it will be green, blue. Okay, so the new one, green, blue, yellow, green, right. So it's a smaller wavelength. So absorbs shorter wavelength of light with the conjugation, which is the alternating single and double carbon to carbon, the alternating single and double bonds, then we are talking about the highest occupied molecular orbital and the lowest unoccupied molecular orbital. If it's the shorter wavelength, that means it's going to be a higher energy, which is going to be a bigger gap. And in this case, it's the larger gap between the HOMO and LUMO, highest occupied and lowest unoccupied. And that's to do with the fact that we've got a shorter conjugated system. When I'm talking about going to a shorter conjugated system, I'm getting that off of the fact that it's a shorter wavelength of light, and then shorter wavelength is higher energy gap. And also the second fact is that the longer the conjugated system, the smaller that gap. If we've got a larger gap, it has to be because of a shorter conjugated system. Next one, we're going to look at the calculation to work out the pH when given the KIN. So one of the bits that's going to be helpful is that pH equals the pKIN plus or minus 1. We are trying to do a range. When we're turning anything into the P version of that, so going from KIN to pKIN, we want minus log to the base 10 of that value. I don't see it in the data booklet, so I wonder if that's just one we're supposed to just have known. So pKIN is going to equal minus log to the base 10 of 7.9 times 10 to the minus 6. Sticking that in the calculator gives us 5.1. So our pH range would be from 1 less than that's 4.1, and 1 more than that be 6.1. That with the range. Different roundings, you'll have it slightly differently when we have our answers there. In question 3, we're asked which type of quantitative analysis that we have. The two options for quantitative analysis is going to be our volumetric or our gravimetric. Volumetrics are things like acid-base titrations, redox, complexometric back titrations, whereas if it's gravimetric, we will either be doing a decomposition or volatilization, where we drive off a product and we measure the masses involved, or as in here, we have our precipitation reaction, where we make a precipitate, we isolate it, and we can measure the mass and do some calculations around that. If the reaction has gone to completion, there will be no more silver left into the seawater. If we add more of our reactant, silver nitrate, we can see if there's any more solid precipitate that's being formed. So we can add more. And if it hasn't finished, we will make more product, and we just keep going. Mass was determined to be this many grams. Calculate the concentration of chloride ions in grams per litre in undiluted seawater. Okay. The precipitate is silver chloride. It's silver 1, so the formula is AgCl. We can work out the number of moles using M over GFM, 0.779 over silver is 107.9. Chloride will be 35.5. That goes 143.4. That gives us 0.005432 moles that we've got for that. Within the silver chloride, there is one chloride within that compound. That means that the moles of chloride will also equal 0.005432. That, importantly, is in 20 centimeters cubed of the solution. And we have to scale that up to 100, and times that by 5. That gives us 0.02717 moles. Then we want to turn that into mass. Well, mass equals N times GFM. I'm going to take that number of moles. I'm going to times it by 35.5. We're not talking about chloride, which would be Cl2. We're we're not talking about chlorine, which should be Cl2. We're talking about chloride, which would be 35.5. When we're trying to do concentration, for this one, we're doing it mass per litre. So we take our mass, and we divide it by the volume of undiluted seawater, which is our 50 centimetres cubed. Turn that into 0.05. That gives me a final answer of 19.3 grams per litre. We could have done it the scaling way as well if we had 0.94535 was from 50 centimetres cubed. We had asked for it per litre, 1,000 centimetres cubed. We divide by 50 times by 100. That's doing the same job as what we've got. In question 4, we're talking about an addition reaction with a halogen halide, hydrogen halide. And that means it's going to go through a carbocation intermediate. So what's going to happen is we're going to break the carbon to carbon double bond, bind to the left hand side, well, to either one of the sides for that, and that makes our carbon that hasn't had the hydrogen attached to it is going to become positive. And then if we're asked to go on forward, well, the bromine is then going to join on, and that's going to form your C2H5Br as it's shown in there. If you're using bromine to react with the alkene, you'd end up with a cyclic intermediate. If there's an increase in stability, that's when the energy would decrease. It's temporary. That feels like it's going to be right in here, just at the little dip in the energy. Next up, explain why thermodynamics, even though there decreases in entropy, it's the total energy. The total entropy is going to increase. That means that the surroundings, the entropy of the surroundings is going to increase. That's what offsets the decrease in entropy in the reactant. So entropy of surroundings is going to increase. The other thing we can look at is it's releasing energy to the surroundings. Again, that will increase the entropy of that. We're asked for the entropy change. So there. And there. Each jump must be 10, so we're at 20 there. And then we're at minus 60. We've dropped by 80. 20 down to 0 and then another 60. So 80 minus 80 kilojoules per mole. Next one, we're trying to find the temperature at which the reaction changes from being feasible to being unfeasible. We're going to be dealing with delta G goes delta H minus T delta S. When we're trying to find out the temperature which changes, delta G is going to equal 0. Now we'll start to rearrange for T. So move the minus delta TS over to the left. That gives T delta S equals delta H. And then divide both sides by delta H, by delta S. Maybe delta H over delta S. T is therefore going to equal. Watch out for our units. We had minus 80 kilojoules per mole. I'm going to put that into minus 80,000 joules per mole. Divide that by the minus 132 joules per Kelvin per mole that we have got for the delta S for the entropy. Pop that in. It's going to come out as a positive value. That'll give us 606 Kelvin. It asks us for Kelvin, so we're all good there. That gives you your final answer for that. We're talking about Markovnikov's rule. We sketch out of propene. Markovnikov's rule is saying that hydrogen goes to hydrogen. That means that when we break the carbon to carbon double and we put on our two new bonds, the hydrogen is going to end up on the left hand carbon, and the bromine is going to go in the middle to make 2-bromopropane. Now, if I actually read the question, it's asking about why that's more important. It's because when we have our intermediate, we have our secondary intermediate, we have our secondary carbocation, which is more stable than the primary carbocation that forms for the other isomer. We have a more stable carbocation intermediate. Okay, so isomers from, first of all, let's go for addition reactions. So as I was talking about for the last question, we have our major product, would be 2-bromo, or we could have the minor product that would be 1-bromo. So combination rule will favour the one that has the more stable carbocation intermediate, and that's where it's going to be primary, secondary, or tertiary carbocation. It's going to do that as well. With this example, we've got the 2-bromo propane and the 1-bromo propane. Next, we can look at the geometric isomers. That will tend to happen when you've got a carbon-carbon double bond or a ring structure that we've got. Cis isomers have both groups on the same side of the carbon-carbon double bond or ring, and trans on opposite sides. So sticking with the bromine, we could have a carbon-carbon double bond, and then I want both my bromines. I'm coming at the top with my hydrogens underneath it, versus one at the top and one off the bottom. Because you can't rotate around the double bond, we can't make them both be on the same side. That's why it's important to have this restriction of the rotation. So this would be cis 1,2 dibromoethane versus trans 1,2 dibromoethane. So they're likely to have different melting points and boiling points, which means you could separate them by distillation. I think I'm right in saying that trans ones tend to be able to pack more tightly together, because this is quite bulky up here to stop them from getting so close together. Whereas here we're kind of separating out the bulk so they can fit more tightly together, increasing the intermolecular forces that we go through. A cis compound might be more likely to undergo an elimination reaction, because both of the bromines in this case that are going to get removed were on the same side, and then we can put a double bond in there. It'd be harder to remove both of them together because they're on opposite sides. Perhaps. We've talked, it also mentions optical isomers. They require a chiral center. We're looking for 4 different groups or atoms or groups of atoms attached to a carbon. And that gives rise to optical isomers or enantiomers. Ties into the chemical. Ties up to one of the multiple choice ones. We have 3 different things attached. That'll do it. Find out wedged. So W coming at the top. I'm going down to the X and come down to the Y. Right to our Z. Something along the lines of that. Non-superimposable mirror images. They will have identical physical properties, except they rotate polarized light in different directions. I couldn't quite get out the correct words. That interactions have to be correct between the active site of the enzyme and the molecule. If those are in different orders, you won't be able to get all three parts of it to line up like we do on the left. The one on the right doesn't have that because the CO2H and the OH are in opposite directions, so it's not going to be able to activate and allow the enzyme to work upon it as well. So I'm trying to get from there. We are asked about how we can isolate them. Ways of isolating chemicals. We talked a bit about the distillation and separating off. One would boil off for the other. You can separate them as well. Another option would be for TLC or thin layer chromatography. Would allow one, if one's more polar because of the way it's arranged, it would then move more in a polar solvent, something like that potentially. That's everything I can think of to put in for this question. To get the 3 marks, you have to give a good answer. Reasonable would get you 2 marks and limited would get you 1 mark. So I hope that would be enough to pick up the 3 marks for that question. Moving on, we're asked about the molecular formula of this chemical, 2-furane methanethol. Let's have a sketch out of it, putting the carbons in. So we have a carbon, going down to an oxygen, coming down to another carbon, carbon, sulfur, carbon down the way, carbon up the way. And then that completes it. So 1, 2, 3, 4. 1, 2, 3, 4 looks good. Pop in the double bonds as we have here. And we have a H coming off of there. So carbon needs to make 4 bonds. That means we're missing a H there, a H there, a H there. We're all good here because it's making 4. We would need 2 H's coming off this one. And we've got our H coming off the sulfur. Counting that up, we have C5. H2, 3, 4, 5, 6, and OS or SO, and this could be in any order of this. We're looking, so in mass spectroscopy, we are splitting up this compound and we're looking for a peak that could be 33. Well, I know that sulfur is 32. If we chop off SH, that's going to give you your 33. Important thing we're doing with our fragments is they should be in squared brackets. But we definitely have to include the fact that that would be a positive fragment for it to then work in, for it to have been produced in mass spec. So all the parts need to make sure they've got a positive charge for a fragment. That gives us our answer for that one. Next up, we're asked about the bond that is responsible for peak at 1710, and we've got a molecular formula now. We can have a wee play around first of all about what types of chemicals we could have. So with a single oxygen, I'm thinking alcohols, ethers, ketones, or aldehydes. So if I was to put in an alcohol, and alcohols and ethers have they will have the same formula. That's not going to work, because we would need 1, 2, 3, 4, 5, 6, 7, 8. So that means it's going to have double bond, which would mean we're dealing with either our aldehyde, because it's at the side, so that would be propanal, or we're dealing with the double bond O in the center, which would make that a ketone, so propanone is where I'm going with that. Now, if the chemical has more carbon, it's maybe not really going to work to start sketching them out, but that's what I'm thinking. 1710. Go in here to the data booklet. Go to our infrared correlation table. 1710. Is it going to be 1 or is it going to be more? Well, it could be this one, this one. I think that's the only 2. It's not a carboxylic acid because that would need C double bond OO. So it's not going to be that. It's going to be an aldehyde or a ketone. It's going to be the C double bond O stretch of that. So identify the bond, C double bond O stretch. Next up, we have to draw a formula for compound A. Well, luckily enough, I have already sketched them out. And this now comes down to the hydrogen environments. So with compound on the left, well, there's a hydrogen in this environment here. We then have a second environment here because we've got a CH2 in between a C double bond OH and a CH3, and then our CH3 beside the CH2 is going to be different, whereas in our propanone you've got CH3 beside a C double bond O, and that is identical on either side, so it's going to be propanone. So we want to have our structure something like this. Next one, compound B contains the same functional group. Predict the number of peaks. Well, I just talked through that. That is going to be 3 peaks. And this is why I should have read the question, because I now need to come back up here and grab this and then do my little highlighting again. So environment 1, environment 2, and environment 3. For that one, shuffling on elemental analysis, we are trying to work out what is the makeup of the chemical we are dealing with. We are completely combusting 1 gram of the sample, carbon, hydrogen, and oxygen. Okay, so first thing we do is going to start with each of the products. So carbon dioxide, and we're going to work out the number of moles. So it's going to be 1.47 divided by, well, carbon dioxide is 44, and N equals 0.0334. Let's go 334 moles. And to work out the mass of carbon that is in that, well, there's 1 carbon within 1 mole of CO2, so there'll be 0.033 moles of carbon within 0.033 moles of carbon dioxide. So I just want to times that number by 12 to turn it into the mass of carbon this time. This is where writing down and keeping track of what each number is very helpful for you and for your marker, so they can get to grips with what's going on. Onto the hydrogen in the water, what's going to be the 0.6 grams over 18 for that. 0.6 over 18, 0. Lots of 3s, so 0.333 3s for that. And then the mass of hydrogen within one water there are 2 hydrogens. We're going to have to double up the moles, and it's going to be 0.0666, and then we're going to times that by 1 because hydrogen is 1, so that will give us 0. Try that again. 0.0666. If the total mass is 1 gram, then our mass of oxygen will equal our total mass, take away both the masses of the carbon and the hydrogen. That gives us 0.53 grams of oxygen. Next up, we need to look for the moles of each of the chemicals. So we have got our C to H to O. Importantly here, we already know the mass. Nope, we already know the moles of the carbon is 0.0334, and hydrogen was 0.0333, pretty much the same. Now when it comes to the oxygen, well, I know the mass of oxygen is 0.53. When it comes to the empirical formula, we are dealing with the mass of 1 atom of it. So because it's oxygen, we're going to divide it by 16 in this case. That's going to give us 0.0331 moles. As a recap, we already had worked out the number of moles of the carbon dioxide, and there's one carbon within that, which is why it's the same. We're taking into account there's H2O, which is why I've doubled it, and I've just done the same calculation, but for oxygen, given 0.0331. In this question, I would say the numbers are pretty lined up. I think the combination between the chemicals is quite clear, that the first and the last ones are the same, and this is twice as big as we had. And empirical formula is the smallest ratio of each atoms. We have one carbon, two hydrogens, and one oxygen for CH2O as the empirical formula. Okay, in this one, we're talking about solvent extraction. This is when we would use a separating funnel. Right, so what do we need to do then? So we want to mix the coffee with the dichloromethane in a separating funnel. Then you need to allow it to settle. Now, does it tell us which one's heavier? Now, it doesn't look like it tells you, but I suppose if you think about the mass of dichloromethane, there's two chlorines, which would be 71 plus the C plus the carbons versus water. So in the aqueous solution, we're just adding water. So the dichloromethane would be the lower level. We're going to run off the lower layer, which should be our solvent, the dichloromethane layer. And then we want to repeat extraction with more solvent, so more dichloromethane. If you do lots of smaller extracts rather than one big extract, you get more of the chemical pulled off as it goes. Next up, we're asked to calculate the value of the equilibrium constant. So our K is going to equal the caffeine in the dichloromethane divided by caffeine in the aqueous layer. Importantly here, this is the total caffeine that we have got. So the top layer and bottom layer added together would give us that number. Dichloromethane has 0.136. And that means if we take them away, we'd have 0.014 grams in the bottom layer. 0.136 divided by 0.014 gives us an equilibrium constant of 9.71. They have no units. That's just what we put for our final answer. Next one, talking about thin layer chromatography, determining that it's an impure sample. Well, first of all, you've got to have a dot at the caffeine level, otherwise you've not made any of it at all. So as best we can, have it lined up just in here. And then there's got to be at least one other chemical involved. That could be higher or that could be lower. Just for easiness, let's just do it in line with that S. So I've got a reference point. So this would mean we have at least made some caffeine, but we've also got something else sitting in the sample. Next up, we're asked about making up a stock solution. 0.1. Okay. So we're going from 0.2. Well, if we divided it by 2, we'd get 0.1. Divide it by 20 would give you 0.01. 20th of your final volume has to be our original chemical. So 1/20th of 500 would be 25 centimeters cubed. So what we're going to have to do is take 25 centimeters cubed. That's of our stock or our original solution. Is pipetted into a standard or volumetric flask. And flask made up to line with deionized or distilled water. That should pick up the marks for that. Next one, we're asked to work out the mass of iron in one tablet. So iron is going to be the final thing we're going to deal with, and we're dealing with Fe2+. That means we're going to need to start with the other chemical, which is potassium permanganate, which is manganate part MnO4 minus. Okay, so what are we told? We're told the concentration and we're told the volume. So that means that N equals C times V. So N equals 0 0.01 times 0 0.0118 divided 11.8 by 1,000. That gives us 1.18 times 10 minus 4 moles. And importantly, that was a 25 centimeter cubed sample, but in the whole entire thing, it was 250. So that must mean it's going to be 10 times bigger. So 1.18 times 10 to the minus 3 moles in the whole entire flask. Now, we need to at some point times it by 10. I would much rather get it done and dusted out the way before I forget. Next, we need to look at the ratio. So from MnO4 minus to Fe2 plus, that is a 1 to 5 ratio, which is 1.18 times 10 to minus 3 is 5.9 times 10 to the minus 3 moles of that. We're asked to work out the mass. So M equals N times GFM. So M equals the 5.9 times 10 to the minus 3 times, I think it's 56.8. 55.8 gives us a mass of 0.329 grams. Are we done? Not quite. So that's in 5 tablets. So let's divide that by 5. We tell you what 1 tablet would be. It's also milligrams, oh for goodness sake. Okay, so that would be 0.0658 grams. Or milligrams. Well, 1 gram is 1,000 milligrams. So we can do 65.8 milligrams as our final answer. That would be there. So at some point we have to times by 10 to scale it up. We also have to divide by 5. We could have done that at any point and still ran it through and we'd have got the same answer. But that's the way I would tackle that one. Shuffling on takes us to next question here. What have we got here? So we're dealing with Cl is SO4 2 minus for sulfate for that. Now, from previously in chemistry, should be aware that that's an oxidizing agent. Just that would. Yeah, I'm not sure the exact reasoning here, but I'm taking it to be something to do with it being an oxidizing agent. If we look over here, the chlorines on the opposite side, they two could react with each other, whereas the sulfate is on the same side. Is that? So, asking my mind back, thinking higher chemistry, then they two would react together in a redox reaction. I'm going to go for... I'm kind of bringing some previous knowledge in that, but it does kind of make sense that if one of them is on the right hand side, like the Cl minus, the sulfate's on the left hand side, they act differently for this one. In this one, we're talking about why a transition metal complex is green. So it's all, again, to do complementary colours. So looking in our colour wheel, purple is complementary to green. So if it appears green, that means that it absorbs purple. So it absorbs purple light. And then when it's transition metal complexes, it's to do with electrons moving to higher d orbitals. Electrons move to higher d orbitals. Comes back to what we said about earlier, where your d orbitals would be split in order for an electron to get promoted to a higher energy they must absorb energy. That's when the purple light's coming in for that one. Next up. Okay. Why can this be turned amphoteric? So amphoteric means it can act as both a base and as a acid. Acid and a base is a proton donor and a proton acceptor. I can do both those things. In question 7, we're asked to identify the second compound that is produced in this reaction. What I want to try and get a head around is what have we got. First, going to look at what we have dealt with in the dopamine. So we have our ring, we have a carbon coming up, carbon coming down, then our NH2. That's going to be this one here, one carbon up, carbon down, and I think they're trying to trick us by making the NH2 group come off up to the right in the dopamine, but on the levo dopa, it's coming off at the bottom of it, but it's still connected in the same way. That leaves us with some carbon. This is going to leave us with carbon double bonded to an oxygen with an OH group. Okay, so what's happening is in the levodopa, we're cutting off this section here. There's going to have to be a hydrogen on the end of there. Now that would likely be the hydrogen, or is the hydrogen from the OH group, as that's getting cleaved off and getting separated off. That's looking to me as if we've got carbon and 2 oxygens. And I've just noticed an even more obvious way that that's true. If you just look at the difference from the starting material to one of the products, there's 1 carbon missing. All the hydrogens are taken care of, because when you slice off the COO, you have to put a hydrogen there to make this carbon make the correct number of bonds. And then we're missing 2 oxygens as well. So that's looking like it's just carbon dioxide. So if I'd clocked those formulas earlier, that would make this even easier and even quicker to deal with. But it's definitely this bit that's removed. We just need to be careful that it's the hydrogen is actually going to be on the end of the dopamine. So the hydrogen is going to be attached to the dopamine here. Yeah, in this next part, we're asked to deal with some concentrations. Okay, so we are asked about the remaining percentage. Well, we're starting off with all of it, 100%, and we're losing 29.5%. So that will be 70.5% remaining. So it was 125 milligrams. Let's work out 70.5% of that. 88.125 milligrams. We are using, we want to get to moles. So I'm going to do N equals M over GFM. I'm going to convert the milligrams into grams. It'd be 88.125 times 10 to the minus 3 divided by 1,000. And that's over the 197. That will equal 4.473350 times 10 to the minus 4 moles. And to get concentration equals number of moles over volume. Our answer from 4 and divided by the volume, which is 4.35. And that gives a concentration of 1.03 times 10 to the minus 4 moles per litre for that part. Next up, we're talking about classifications of drugs. This will typically be your agonist or antagonist to prevent something from being broken down. So an agonist mimics the natural substance, not doing that. Antagonist blocks the receptor. So it's actually not either of those two. It is stopping an enzyme from working. So it's inhibiting the enzyme. So in all the time that I was teaching, it would be agonist or antagonist were the answers to these types of questions. It's always been part of the course that enzyme inhibitors are something we need to know about. It just seems to be more commonly in the rotation now for the answers in the exam. So in this one, it would be an enzyme inhibitor because it's acting upon an enzyme. It's not acting upon the receptors. If you'd done higher biology or higher human, you would have talked about enzyme inhibitors and blocking the active site. And this is the application here in this particular chemical. Next one, we're asked about the hydrogen bonds. The hydrogen bond acceptor is an atom with a lone pair of electrons that can form a hydrogen bond. Determine the number of hydrogen bond acceptors in the carbidopa. So something we need to think about is we need to go back and think about when we were doing the electron arrangements back in the day. Well, oxygen is in group 6, so has 6 electrons. That means every oxygen is going to have 2 lone pairs, and these are the electrons that would be bonding to, if we take this example here, it's bonding to the hydrogen and it's bonding to the carbon. We would end up with 2 lone pairs of electrons there, 2 on that one, 2 on that one, and then 2 on that one. Carbon makes 4 bonds, and it's got 4 outer electrons, so it's going to have no lone pairs within them, so we can ignore all the carbons. Hydrogen makes 1 bond that has 1 electron, so again, don't need to worry about that. That one's not going to take, that one's not going to have any lone pairs. Nitrogen, however, will do, because nitrogen is in group 5, which means it would have 1 lone pair, and it's why it makes 3 bonds to things. So if you look at both of the nitrogens, they both are making 3 bonds. That means each of them is going to have a lone pair. So we've got 2, 4, 6, 8, 9, 10 pairs.
No.
I definitely misread that question. I was counting up how many lone pairs they've got. Not saying that, it's saying how many groups are available to make hydrogen bonds. So that each of the oxygens and each of the nitrogens, so it doesn't matter how many lone pairs they've got, just the fact that they've got lone pairs means we can count them up, and that'll give us an answer of 6 hydrogen bond acceptors. So 1, 2, 3, 4, 5, 6. So I just misread that. It's not about how many hydrogen bonds can be formed, not how many lone pairs, how many parts of the molecule are able to do this. That'd be 6 for that question. Here we're dealing with E equals LHC over lambda. The constants that we need are on page 20 with all the units as well. If you're not sure how to turn nanometers into meters, we can use the conversion on the same page. So nano is times 10 to the minus 9. If you're going from nano to meters, you just put that on the end of your number. Okay, let's get it set up. So L is Avogadro's constant, which is 6.02 times 10 to the 23, times Planck's constant, which is 6.63 times 10 to the minus 34. The speed of light is going to be 3 times 10 to the power of 8, all over 471 times 10 to the minus 9. That gives 25422 joules per mole, which equals, divide that by 1,000, 254 kilojoules per mole. One thing that this question does is it flags up some of the issues that can happen using different types of calculator. Notably, one of the more recent updates, and that's the FX. Well, I've got the FX 85GT, the one on the left there for the. I have inputted these the same. I've put both of the values in brackets. I've used 10 to the power of button, and I've divided them by the wavelength. But they're giving you wildly different answers. The solution seems to be, if we use the fraction button, I'll just quickly pop that in. So now, having used the fraction button, I get the same number out on both of them. It may well be, if you find you're sometimes getting questions wrong, other times getting them right, it might well be just the format you're putting in. Calculator just isn't able to process it properly. What I would strongly suggest doing is take your calculator, get it set up the way you would in the exam, and just make sure that however you like to input your calculations is going to give you the correct answer. So I've always been, I put the top line in brackets, then hit divide by whatever the bottom line is, and that works on certain calculators, no problem. But I have to be mindful of, if someone has a different calculator, or if I'm using a different calculator, it might flag up a problem. In these energy questions, we're talking through wavelengths of light in the visible spectrum. We should be looking for some sort of 3-digit energy per mole associated with it. That can be a warning sign that we've maybe done something wrong. It could just come down to us typing in the values wrongly. That will also mess it up as well. But calculators can be an issue. It may well be using one of the older models of the calculator avoids those problems. It might well be that even newer calculators have updated and fixed that problem. Just make sure you can use your calculator to get the correct answers out of questions similar to this. Away from calculators, we are now going to look at curly arrow notation. Complete the equation using curly arrow notation to show how a carbon-carbon bond undergoing homolytic fission creates two free radicals. Now, when it comes to homolytic, we're dealing with the same splitting. That means each of the products has taken one electron from the bond. So in here there would be 2 electrons. If we're doing a single electron, we want a single-headed arrow. We want one single-headed arrow going to that carbon, and we want one single-headed arrow going to the other one. I don't know if it matters if you have them both at the top, or one at the top, one at the bottom. I prefer this way just because it's neater and it keeps them all from overlapping with each other. But it's a single-headed arrow going from the middle to the right chemical, and then middle to the left chemical, and that's how those work from there. Next question is asking us why this is not commonly used. Part of the problem will be that radicals are very reactive, so they will end up reacting with other chemicals. It's harder to control them. There'll be side reactions possible. Tied into that, there'll be a mixture of products. So if we took our chemical, let's say that we had 3 hydrogens on that one, we just make 1 carbon here. But when you split that up, you're going to have 2 different radicals, which would then react differently with other chemicals. So you might be adding on ethyl groups instead of methyl groups. This is our second using your knowledge of chemistry question, where we're looking to give a good answer for all 3, a reasonable answer for 2, and a limited answer for 1. First thing I do is let's talk about orbital box notation. And that shows how electrons fill orbitals, atomic orbitals. So it's able to show Aufbau's principle where 1s is filled before 2s, so it fills in order of increasing energy. We can also look at Hund's rule of maximum multiplicity, and that's where the electrons fill orbitals singly before pairing. The Pauli exclusion principle, where no 2 electrons can have the same 4 quantum numbers, they have to have opposite spins. Going into a second type of notation, we can use spectroscopic notation, which is the 1s2, 2s2, 2p6, and onwards from that. I'm saying it's going to be easier to compare different chemicals because it's more at a glance. You can see the differences between them. So if the second one had 2p4 or whatever it might be, so in my opinion, easier to explain trends in the periodic table. And then actually rolling back to the orbital box one, that makes it easier to see or to visualize half-filled and filled subshells. You'll see that instantly. So if we're using the spectroscopic, we need to remember that P has 3 boxes, can hold a maximum of 6. So here it is a filled one. Whereas if I go back up to the top, if I tweak this slightly, you can see that's got the maximum in there from that, if I do it that kind of way. Now the other type that I'm thinking of would be like our dot cross electrons represented by dots to show them. My first instinct though is that's too nat 5 I don't know if this is going to be credited with information, but let's go for it anyway. Electron and be. So, for example, if we're thinking back to when we're talking about carbon, carbon has 4 outer electrons. That means that we're going to end up with likely a tetrahedral shape. If it very much depends on what you're joining onto. So if we have hydrogen, CH4 will be tetrahedral, but something like CO2 is linear because of the way the double bonds take up 2 of the like blah 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 blah. Again, I'm not really feeling this as a proper advanced higher level answer. There's possibly a way of dealing with it, perhaps showing how they join together and things like that as well. Limitation wise, apart from it being from that 5, the limitation of that is it doesn't show the subshells and individual orbitals. If you had something there, you'd have 8 electrons in the second, like in the second shell for that, because it doesn't distinguish between 2s and 2p for that. There may well be something that I'm completely missing. I would still hope that this would be a good enough answer to pick up the 3 marks. Wouldn't really argue if it was getting reasonable. I'd probably argue against limited for that. So yeah, there might be other things that spring to your mind that I've just not picked up on, but that's what I would put for that one. Next one, we're dealing with a percentage by volume that we're trying to react with a certain chemical. Okay, so job 1 I would say would be work out the number of moles. So there's 197. And then we are doing a ratio between these two. So AU to NaCN. Well, if it's 2 to 4, that's 1 to 2. Means I need to double our answer here. Right, couple of things going on here. So the first thing I think this is percentage by mass. Or weight, but by mass. That means that 0.055 grams in 100 centimeters cubed. And then what we need to do is turn this into a mass. So mass equals N times GFM. Mass will be our 0.010152 times sodium, carbon, and nitrogen. Sodium 23, carbon 12, and nitrogen 14. I'm making that 49. Mass 0.497448 grams. So from this, 0.055 grams would be in 100 centimeters cubed. We need to get to 0.497448. If we have set up this kind of proportion thing, if we divide 0.055 by itself, we get to 1. And if we times 1 by the 0.497448, we get to that. Divide by the first, times by the second. 7448. And then we do the same. Then we do the same to the 100. So 100 divided by 0.055 times 0.497448 gets us an answer of 900. Wee bit around in 4 centimeters cubed. If the question was dealing with the percentage by volume, it would have been that many centimeters cubed in 100 centimeters cubed of solution. The way that the reason I went for the by mass one was because we weren't given any volumes to do with any of the chemicals, so that's going to be no good to us there. There might be another reason why it's that, but we're dealing with a mass, turning it into moles, worked out the mass of the worked out the mass of the NaCN, and then a bit of scaling to get us our answer. Next one's asking about the coordination number. That's the total number of bonds from the metal to the ligands. That is the total number of bonds from ligands to the metal. And where that's important is if you had, let's say, a bidentate ligand making 2 bonds. Well, if you had 2 of them, well, that's going to be 4 bonds in total, coordination number of 4. If you had, if we had a monodentate ligand, monodentate means they make 1 bond. But if you had 4 of them, well, then you'd get a total of 4 bonds as well. So for coordination number, it doesn't matter where the bonds are coming from. It's just that there are X amount of connections from the ligands to the metal. Here we're dealing with our naming of a complex. So let's start us off. What have we got first though? So I'd start with the ligand. The ligand is cyanide, which would be cyanido. There's 2 of them. So it's going to be dicyanide. It's gold, but overall it's a negative ion. That's when you use the changed name, which they have helpfully told us is aurate. If this was positive, we would just write gold. Next thing we need to do is work out the charge on the gold. What it's saying is overall 1 minus charge on the whole complex. Cyanido is Cn negative. We have got 2 of them, which means we've got 2 minus coming from the cyanidos. How would you get -1 overall? Well, the only way that would work is if the if the gold was 1 positive, that would give you an overall 1 minus charge. The metals will always be positive. So let's say you might have been in this position where you're not sure what charge is on the cyanido. If that was 0, the only way you could get 1 minus overall would be for it to be gold 1 minus. But that's not what's happening here. The gold is going to be positive, and in this case it's going to be +1. So dicyanide aurate 1 would pick up the mark for that one. In this question we've got AuCN2 minus turning into Au. Now that is the same chemical. Okay, good. So we figured out that Au was 1 plus, and it's turning into a metal which has no charge. How's that going to work? Well, it's going to have gained electrons, and that's going to go from 1 plus to no plus, and then from oil rig from back in the day, that makes that a reduction reaction. The other thing we could do is look at the oxidation state. We have got +1 going to 0. That value is going down. That's going to be a reduction reaction. Another thing we could do is we could look at the electrochemical series. These are all reduction reactions where we're going from a positive ion to a neutral atom. That is matching what we've got there. So that's 3 ways we could get that as well. We are doing a precipitation reaction, and we want a pure dry sample of the gold metal. So what is this trying to show? Well, we're starting off, we have our precipitate. We're going to remove that from the leftover solution. One of the things I've not shown there is we can rinse it. So filter and rinse. And the residue is the bit that's left behind, the bit that should hopefully be our gold. Next thing I wanted to do is we want to heat to a constant mass. That way we've dried off. That means we'll have no water in it, which we're asked to do. I've got here a desiccator. Desiccators allow you to cool it down without any water being reabsorbed, so it prevents the reabsorption of water. If you didn't do that and you just left it to dry out on the desk, well, it would absorb water, which would mean that your mass would keep going up. So it's more difficult to get to a constant mass if you don't use a desiccator for that. But whether that's needed in the answer, I'm not sure. I think that's what I would do. And just keep going until you get this mass that doesn't change anymore because all the water has been driven off. This one, we're talking about parts per million. And parts per million is milligrams per kilogram or milligrams per litre. So let's write that. So milligrams per litre or milligrams per kilograms. Most of the questions ask you about per kilogram. It's asking us for a mass in kilograms, which is again why I'm leaning towards that one. Okay, so we have got 21.5 milligrams per kilogram. We want to get to 1 gram. So let's do a little bit of conversion. So a milligram is 1,000 times smaller. So it'd be 21.5 times 10 to the minus 3 grams per kilogram. So to go from 21.5 times 10 to the minus 3 down to 1, we'll divide by itself, divide by that number. So 1 gram of gold would come from, that's 1 kilogram, so 1 divided by 21.5 times 10 to the minus 3. So that would be 46.5 kilograms of rock. Now, I'm just cutting it on here. I missed the fact that's 91.5% efficiency, the percentage yield. So we can actually make that work though. Now, the mass that I've worked out there, that would be our 91.5%. It's 46.5 kilograms. We are going to need more than 46.5 kilograms because it's not 100% efficient. Just rinse and repeat. We're going to divide by 91.5, then times by 100. So we're going to do that to the 46.5, divide by 91.5, times by 100. That gives 50.8 kilograms. Could have done some of the steps in a different order, but that's what we need to do. Next up, we're asked about carbonyl compounds. Going from an aldehyde to an alcohol is going to be a reduction reaction. And then a reagent that's really good for that is lithium aluminium hydride. LiAlH4 is its formula. What is happening in, what type of reaction is taking place in step 1? Well, dichromate is an oxidizing agent down towards the bottom left of the electrochemical series. If it's an oxidizing agent, it will oxidize the aldehyde. So that hopefully going to be oxidation. I'm seeing what they're doing here because if that's oxidized, that will then become an carboxylic acid, so methyl propanoic acid. And then if you have an alcohol and a carboxylic acid, you will make an ester. And that is what we're being asked to do. So draw the structure for compound Y. That's going to be a ester. Now, how I would sketch this out. So we point our functional groups at each other. Oh, and then it was, what was it again? Methyl propanoic acid. We need to remember that we're going to be making water when we're making an ester. It's a condensation reaction. So then what will happen is we'll remove them. We're going to plonk them together. And we have our ester link. We have our ester. Double and checking. So CH3, yep. CH with CH3, yep. C with 2 H's, O. Double bond O. Methyl group off the second bit there. And that would work out for that one. Because it says structural, we can shorten them down. So if you prefer to write it as CH3, CH, CH3, and so on, you can. I've got a kind of combination of full and shortened structures. It said full, we have to show all the lines. If it did say that. Next one, we're looking for an alpha hydrogen. Our carbonyl group is C double bond O. We're looking for the carbon next to that, which would be this one here. And it's any of the hydrogens attached to that, which would give us these two hydrogens there. Our next question wants us to find an isomer that will not carry out an aldol reaction. So it will not have an alpha hydrogen. What we could do then is, well, if we take a carbon off the left-hand side and put it coming off at the top, well, that blocks off the potential site here. And if we do the same at the bottom, now the carbon next to the carbonyl group has no hydrogens on it, so it won't be able to carry out this reaction. Double check that we've got the same number of carbons and hydrogens. There should be 5 carbons. Tick. This has got 1, 2, 3, 4, 5, 6, 7, 8, 9. This has 10 hydrogens. My one, 3, 6, 7, 8, 9, 10 as well. So that looks like that should work out. Next up, we have to draw a structural formula for the product formed in the aldol reaction between two molecules of this. Are we just supposed to know? Okay, right. So they're asking us to do the same sort of reaction for propanone. Right, let's just set it up in the same way. Now, I'm going to draw this out a little bit awkwardly. I'm trying to keep the same sort of formatting. Right, so what is actually going on now? Let's start with the one on the left. The one on the left stays basically the same, doesn't it? But, so what's happening in this one? Well, the double bond O is going to become a single bond OH. And I think that's the only difference, is this H stays where it is. So that means for our one, our CH3 will stay where it is, right hand side. The C double bond O and C to H stays the same, so that looks like that will stay the same. But instead of having CH3, we've now got CH2, like so, and then that gets bonded to that carbon, or that. I'm going to rewrite this and just tidy it up just so it looks a wee bit nicer, and I'll go through it again. So our main difference is that instead of having H's there, we have then got CH3s in there, which means when it moves across the way, that becomes a CH3 and that becomes a CH3. Now, ignoring the connectivity just now, I have got C double bond O to CH3. I've got a C with 2 H's. I've got my OH with the CH3, and I've got my CH3 on the end. So that would be my answer for that one. It's obviously different from me. I can scribble around. If I make a complete mess of it, I can fix it. Drawing stuff out again, so you've still got the blank page to deal with, is something that will be helpful. Line it up as best you can, even if it means you're drawing out your propanones in a weird and wonderful shape. It makes it easier because it's easier to spot what's happening as you move forward. Next one, we're asked about why 2 isomers would be found in this one. And the only thing I can think of is the fact that it was to do with the carbon beside the carbonyl group. So here, we've got 2 carbons beside the carbonyl group, each which have hydrogens available to undergo that reaction. They're present on position 1 and position 3 of the chain. Now we've got a big long chemical to name. Let's go for the longest chain of carbons. 1, 2, 3, 4, 5, 6, 7. I'm hunting for any other ways that we can make a longer chain. We cannot. So that's going to be 1, 2, 3, 4, 7's hept. It's going to be heptanone because it's an ketone. So heptanone. Specifically, if we think of the numbers, that's on position 3. It takes priority for numbering. Should be hex 3 on. What then do we have? We have, off of carbon 5, we have a methyl group and a hydroxyl group. When it comes to the naming, we're doing them in alphabetical order. So hydroxy comes first. So 5-hydroxy, 5-methyl. And that would work out there. It's alphabetical by name, ignoring if there was any like dis and tris, it doesn't matter. It's still alphabetical by the name of the branch that's coming off. So 5-hydroxy, 5-methyl, heptan, 3-one, all put together. And this one we're trying to determine the order of the reaction with respect to the Na2SO, Na2S2O3, so the thiosulfate. We want to isolate two reactions where the only difference is the concentration of the sodium thiosulfate. So that's looking good for 1 and 2. What have we done? Well, if we go from here to here, we are doubling the concentration. Watch out for your powers. That's telling me that we're doubling them. And in terms of the rate is also doubling. If you double the rate and double the concentration, that's going to be first order. Zero order with respect to HCl. We can actually see that by, if you compare experiments 2 and experiments 3, as you double the concentration, nothing happens to the rate. So that's backing up what I said. If it's zero order, the rate is not affected by the concentration. So we're wanting just a flat line coming across. I think it could be kind of anywhere just above halfway line. It's not changing at all. That would be our answer for that one. When it comes to our rate equation, this isn't one of the ones that's in the data booklet. We just have to know that rate equals the rate constant, which is K, then the concentration of, we're going to ignore the HCl that has a rate order of 0. We just write the formula in squared brackets as the concentration of sodium thiosulfate. And then because it's first order, it's to the power of 1, which we can just ignore. If it was second order, we'd put to the power of 2, but we don't have to do anything for there. Calculate the value for the rate constant, including the appropriate units. Well, if we rearrange this, K will equal rate over the concentration of the sodium thiosulfate, like so. We can pick any of the reactions, it doesn't matter. I'm just going to go for the bottom two because they're there. So 1 times 10 to the minus 1, 1.31 times 10 to the minus 2, and the calculator it goes. That is 0.131. When it comes to the units, let's look at what we've got. We've got rate as moles per litres per second, and then concentrations in moles per litre. Do that over here first of all. So we had moles per litre per second over moles per litre. We have moles per litre on top and on the bottom. They will cancel out to leave seconds to the minus 1 as our answer. If you had things that were to the power of 2, or if there was multiple chemicals involved, there's going to be more cancelling around, but you're looking for values that can cancel out to leave as our unit. Some people prefer to just memorise that if it's first order, it's this. If it's second order, it's this. Very much, I just work it out at the time, and that works for me. On to the last part. Last question, we're asked to determine the form in which SA exists at a temperature of 100 degrees. Let's run up 100 degrees. That's 100 degrees and 10 to the power of 0. That would be monoclinic. Now that does seem like a very straightforward question. Maybe they're feeling bad for us. That's monoclinic, followed up by a triple point on a phase diagram, shows the temperature and pressure at which all three forms exist in equilibrium with each other. And we're asked about rhombic, monoclinic, and vapor. So monovapor clinic. We're just looking at that point and that crosses over. That's going to be this one here. For that, and then last up, determine the three forms that can never exist in equilibrium with each other. Well, here we've got rhombic, monoclinic, and vapor. That is a possibility. Here we've got monoclinic, liquid, and vapor. And then up here we've got liquid, monoclinic, and rhombic. So monoclinic's the one that is common to all of those points. So it's the 3 excluding the monoclinic. So that would be rhombic, got them already, liquid and vapor. And that brings us to the end of the paper. That's how I'd approach each of the questions. Thanks for watching. Goodbye.